Hello and welcome to today's lesson on redshift, which is part of the space physics topic in GCSE Separate Science physics. So in today's lesson we're going to try to detail the experimental evidence of the expansion of the universe. So if we've been successful and learned in today's lesson, we should be able to understand what the redshift is, understand what the expansion of the universe is, and then finally describe how the expansion of the universe was proven with electromagnetic waves. So in today's lesson we're going to look at the following part of the GCSE Separate Science only part of the specification in physics, which is 4.8.2 redshift. Now the colour of light is the human interpretation of the wavelength or the frequency of light. Now it's how humans differentiate between different wavelengths and frequencies of electromagnetic radiation. Now it's acceptable to discuss colour in terms of either frequency or wavelength, but it's easy to visualise changing colour as changing wavelengths. However, you could also visualise changing colour as changing frequencies. Now blue light is visible light with a short wavelength or high frequency. So light with the wavelength too short to be detected by our eyes is called ultraviolet or very blue. So we interpret short wavelength visible light as blue. Now we interpret very short wavelength visible light as ultraviolet. So this isn't detectable with our eyes. Now red light is visible light with a long wavelength or short frequency. Now therefore we interpret long wavelength visible light as red. So light with the wavelength too long to be detected by our eyes is called infrared, literally beyond red. So we interpret very long wavelength light as infrared, which is not detectable with our eyes. So visible light is an electromagnetic wave and it's part of the electromagnetic spectrum. So the visible light is the part of the electromagnetic spectrum which can be detected by our eyes. Now visible light has a higher frequency than infrared radiation but a lower frequency than ultraviolet radiation. But conversely, visible light has a shorter wavelength than infrared radiation but a longer wavelength than ultraviolet radiation. So visible light can be split up into different sections depending on their wavelength or frequency. So you can split them up into the different colours, which is what we as humans interpret it as. So red light has a long wavelength but low frequency for visible light, so the radiation beyond the red spectrum is called the infrared, whilst blue light has a short wavelength but a high frequency for visible light, so radiation beyond the blue spectrum is called ultraviolet. So each colour within the visible light spectrum has its own narrow band of wavelength and frequency. Red light is visible light with a long wavelength or short frequency. Light with the wavelength too long to be detected by our eyes is called infrared, whilst blue light is visible light with a short wavelength or high frequency. Now light with a wavelength too short to be detected by our eyes is called ultraviolet. So we can see in the following table the different wavelengths of the colours of light. Now really you should try and memorise the different prefixes for your examination, so you should know that in this table we have nanometers, which means 10 to the minus 9 meters. Now our understanding on the physics of colour becomes very useful when studying galaxies in the distant universe. Now remember that the distant universe is also taking a look at the early universe, as it takes time for light to reach us as it is an electromagnetic wave. Now the first scientist to truly look at galaxies was a famous scientist called Edwin Hubble. Now Edwin Hubble was hired to work at the Mount Wilson Observatory in 1919 as a junior astronomer, and the most pressing question of the day concerned the nature of cloudy patches observed called nebulae. Now most of Hubble's colleagues at Mount Wilson thought that they were all in the Milky Way, but he wasn't so sure. So he succeeded in answering the question of where these nebulae were by taking the best possible photos of these objects, and with this he provided convincing evidence that at least some of them were well beyond the Milky Way. So with his work, Hubble had proved that we live in a galaxy, the Milky Way, in our own universe. So it's important that he did this in 1923 by measuring the brightness of what we call separate variable stars, stars which vary in brightness in a regular cycle. And as well as that, Hubble classified the different galaxies in the night sky, and Hubble even came up with the classification system for galaxies which we use today. So Hubble classified galaxies into three categories: elliptical, spiral and barred spiral. Now our Milky Milky Way galaxy is a barred spiral where we live on the Orion spiral arm of the Milky Way, sometimes called Orion's belt. Now, Edwin Hubble then calculated the distance to these galaxies using the latest telescopes of the time. Now, he did this by a method called standard candles. Now, these are astronomical events which have the same brightness, so you could work out by them being further away, they will be less bright, so you can work out their distances. Now, the most obvious example of a standard candle are supernova explosions because they're the brightest events in the night sky. Now, when Hubble measured the colour of very, very distant galaxies, he noticed an interesting effect. He realised that the distant galaxies had a redder electromagnetic wave output than what was theorised to be the case from laboratory experiments. So he realised the more distant a galaxy was from Earth, the redder its electromagnetic waves were compared to what we thought they should be. Now, he originally thought that we might have understood certain stellar phenomena, but actually all the galaxies he observed showed this effect. So the galaxies appeared redder than they should do. Now, it's important to note that they don't actually appear red unless they are a very distant galaxy. So Hubble called these ideas redshift. All the galaxies in the universe were redshifting from Earth. So Hubble then realized that the further a galaxy was from Earth, the more it is redshifting. Now, we can look and work out the effect of redshifting by looking at the light a star is giving out, a galaxy is given out. So we call this the emission spectra. So if we know what the star or galaxy is like, we know what its emission spectrum must be. So we can then compare the observed emission spectrum with what the emission spectrum should be. Now, interestingly, the black lines on these emission spectrum diagrams are caused by electrons in the atoms of an element moving down energy levels and releasing energy. So this again is revision from physics paper 1. Now, redshift is literally the shift of the spectral emission lines to the redder side of the visible spectrum. So you'll notice the pattern of the black lines on the laboratory reference that you can see in the star, the galaxy, and the more distant galaxy. Those black lines are shifting towards the red part of the visible light spectrum. So compared to stationary sources, we could see that the wavelength of visible light was stretching out and therefore the light was appearing redder. So that's a very important idea. So when distant galaxies were observed in the universe, their electromagnetic waves emitted were shifted to the redder parts of the visible spectrum compared to reference points in the lab. So this was called redshift. Now, the major example of redshift observed in the universe is with the distant galaxies. So not all of the galaxies look red, rather they are redder than they should be. So the observation of redshift occurs because we believe the universe itself is expanding. So you can see in the right hand corner here a visual representation of redshift, which is the effect when it is light, or the Doppler effect when this is in fact sound waves. So it's a very important idea. You can see that when you have movement here, you can get stretched waves, which is redder light, over moving towards you, bunched waves, which is bluer light. So let's just clarify what's going on. Light emitted from distant galaxies travels towards us, so we can interpret this wave as electromagnetic radiation. So over time, this electromagnetic wave travels towards the Earth, but in this time the space in between the galaxy and the Earth expands, and this causes the wave to expand with it. So this makes the wave have a longer wavelength than it should do, so it makes the radiation appear redder. Now, the further away the galaxy is, the more expansion that can take place, the redder the wave. Now, it's important to note that the expansion of the universe can only happen where there's little matter in between the galaxies. Now, these areas are called the voids of the universe. Now, it's important to note that the solar system is not expanding in size due to the gravitational forces of the Earth, of the Sun and the planets opposing the expansion. The Milky Way, which we are a part of, is not expanding due to the gravitational forces of the stars opposing this expansion. So we don't observe redshift in stars which are in our own galaxy. It has to be the light of distant galaxies, as that light or radiation has travelled through the voids of our universe. Now, if the wavelength of light has expanded so much, it could even expand into the infrared section and be invisible to humans. So actually, to detect distant galaxies who have their emission redshifted a great deal, infrared telescopes are used instead of visible telescopes. So, the fact that every galaxy in the universe is redshifting or moving away from us is proof that the universe is expanding. As the space of the universe is getting bigger in size, the galaxies placed on it are spreading out, so this will cause the light from the galaxies to spread out as well when they travel through the universe. So this means that the light will have a longer wavelength as it's more spread out and will appear redder. So we can show this idea with the following demonstration. You would get a balloon, which is a model of our universe. You would then draw a number of dots on a balloon, and the dots are models of galaxies in the universe. So the dots represent galaxies, not stars. So you would ensure all the dots are 1 centimeter apart and use a ruler to do this. Now you should try to make this uniform in all directions because this is called the cosmological principle. There's no special place in our universe. So the universe is the same in every single direction that you look. Now you can then inflate the balloon, which is a model of the expanding universe, but be careful not to overinflate it and destroy your universe. So in this example, you're providing the expansion force with gas pressure, but in the universe, expansion is provided by the Big Bang and dark energy. Now, very interestingly, we have no clue what dark energy is. It's a big controversy in modern day astronomy. Now, you can observe over time that the spacing between the dots changes, and you can measure the gaps with the ruler. So what happens to the space between the dots? Well, the space between the dots increases because the space is expanding, so therefore the amount of space in the universe is increasing. Is one dot on the balloon special? No one dot is special in the universe. No one galaxy is special in the universe. They are all the same. So imagine the Milky Way was one dot. How would we observe the Milky Way, okay, and how will we observe the other dots as the balloon is inflated? So it would appear that all the galaxies are moving away from the Milky Way. This is this same effect we observed in whatever galaxy you would live in. So don't think that because all objects are redshifting from us makes us the centre. All objects will have this occur them due to Hubble's law. So how would we perceive distant galaxies? Well, for more distant galaxies, the time taken for light to reach us is greater, so the universe will have expanded more, so the redshift will be greater. But the issue with using this idea as a model of expansion for the universe is a couple of reasons why it's not a good idea. In this model, firstly, the dots increase in size. This doesn't happen in the universe because the galaxies are not getting bigger. It's the space in between the galaxies which is increasing. In addition, the universe is not expanding into space like a balloon is expanding into the air, and the galaxies are throughout the universe, not just the surface. So let's just clarify what's going on. The expansion of the universe also causes objects to be moving further away from each other, or recede. Now, the further away objects are, the more space there is to expand between them, and the greater the recession velocity, which we call Hubble's law. So in theory, it's actually possible for distant galaxies to be receding so fast from us that light will reach us as infrared radiation. So this would make the receding object invisible to human detections with our eyes. But in theory, it's possible for very distant galaxies to be receding so fast that light from us will never will never reach us because their recession velocity is greater than the speed of light. So let's just clarify what's going on. The universe is expanding on a large scale. This means the galaxies are moving away from each other. This causes light which travels in the universe to increase in size, or redshift. Now, on a small scale, the universe is not expanding as gravity is holding the objects together. So this means you are not getting any bigger. Now, the universe is getting larger as the universe is everything, so it's not expanding into something, rather it is in fact stretching out. So it will be like going from infinity to infinity plus 1. There's still infinity, but it's just a bit larger. So, as galaxies have their light redshifted, this means that their wavelengths have been stretched out from what it was originally as it's increased in length. This happens because space, and so the light rays in this space have expanded, increasing the wavelength of the light. So you would say that this radiation has been redshifted. Now, the objects do not appear red, but they appear redder. Now, redshift happens if an object is moving away from us. The further away it is, the greater the expansion of space, so the greater it is moving away from us, so the more it has been redshifted, and we call this idea Hubble's law. So when we consider Hubble's law, this implies several ideas about the universe. So Hubble's law states that the recession velocity, how quickly the galaxy is moving away from us, is directly proportional to its distance from Earth. Now we can tell this because the graph of the recession velocity against the distance from Earth is a straight line through the origin. Now the gradient of the line is something called Hubble's constant, so you can work it out by taking the gradient of the line of this particular graph. Now it's also important to note that this effect is due to redshift. Now redshift is due to the space in between the galaxies, known as voids, expanding. So this causes the galaxies to recede from each other with a recession velocity. Now this supports the Big Bang theory of creation for the universe, because the Big Bang model indicates that space should be expanding on a large scale. So we've got to understand what's going on. If we consider two galaxies, Galaxy 1 and Galaxy 2, in between the two galaxies space is expanding, and this causes the galaxies to move away from each other. Now this effect is observed from both galaxies, so that makes it appear that all galaxies are moving away from each individual galaxy in our universe. Now because this is noted in all galaxies, this cosmological principle is obeyed. So it's an illusion that appears that we are in a special place in the universe. The idea of Hubble's law will be observed anywhere. Now, the basic premise of Hubble's law is there's more space in between the galaxies, so there's more expansion, so as a result, the greater the speed at which the galaxies will recede from each other. So, as we said before, as the line for Hubble's law is straight, it assumes that the expansion rate in our universe is occurring at the same rate in all space and time, because we have our directly proportional relationship, because the graph produces a straight line through the origin. But actually, when we look at Hubble's actual data to find Hubble's law, you'll notice a few things. It's not easy to draw a line of best fit with this experimental data. So this shows that it's not a strong correlation of data. So this is a big area of controversy in modern day cosmology. Is Hubble's law accurate, and is there actually a straight line relationship between recession velocity and distance from the Earth? So let's just recap what we've learned so far. There is an observed increase in the wavelength of light from most distant galaxies. The further away the galaxies, the faster they are moving from us, and the bigger the observed increase in wavelength. We call this idea Hubble's law, and this observed redshift provides evidence that space without matter in it is itself expanding. So there is an observed increase in the wavelength of light from the most distant galaxies. The further away the galaxies, the faster they are moving, the bigger the observed increase in wavelength. This effect is called redshift. Now the observed redshift provides evidence that space itself, the universe, is expanding and supports the Big Bang theory. So if we've been successful and learnt in today's lesson, we can understand what the redshift is, we can understand what the expansion of the universe is, and finally we can describe how the expansion of the universe was proven with electromagnetic waves. So I hope you've enjoyed today's lesson on redshift, which forms part of the space physics topic in GCSE Separate Science Physics. Thank you very much for watching this video, and as always, have a lovely day.